looked at the hydrogen atom and we've written down the Schrodinger equation for the hydrogen atom. It's a real atom. It exists in our universe. And we did not attempt to solve the Schrodinger equation for the hydrogen atom because the solution is slightly complicated and there's a lot of algebra involved. And I do not want to trap you in the algebraic acrobatics. I would like you to focus on the physics and the concept. But when you solve the Schrodinger equation, you get solutions. The solutions comprise the radial part, an azimuthal part, and the polar part. So there is one part which we've denoted as R, which shows only how the wave function depends upon radius. And the other part shows how the wave function depends upon the angles. So if you look at the radial solutions, these solutions are indexed by two quantum numbers, n and l. So the first quantum number shows n, the second one shows the value of l, and these wave functions, these radial parts of the wave functions, have some dependence on r. And we also notice that this a0, which is Bohr's radius, shows us where there is maximal probability density of finding the electron if you take into account properly the radial probability density. So we're going to explore the forms of these functions and the angular parts of these wave functions today in the first half of the lecture, and I'm also going to motivate you what are orbitals. So you've studied orbitals in chemistry. How does it stem out and flower out from the Schrodinger equation? And what is the physical insight that quantum mechanics gives you about orbitals? So if you look at the radial parts, each radial part has an exponential factor. E is from minus r over a naught, e is from minus r over 2a naught, e is from minus r over 2a naught. For n equals 3, this changes to e is from minus r over 3a naught. These are also n equals 3 solutions. E is from minus r over 3a naught, etc. Since the energy only depends upon n, the energy does not depend upon L and n. L, therefore, all three of these radial wave functions correspond to the same energy. So, they correspond to degenerate states. So, first of all, there is the exponential decay. Higher the value of n, faster is the decaying space because there is a factor of 3 here, there is a factor of 2 here, there is a factor of 1 here. The second thing that you would notice is, of course, there is a normalization constant with each one of these radial wave functions because you want to keep the radial probability densities summed up over all volume equal to 1. But each exponential factor is being multiplied by a term that is inside these parentheses or square brackets. Here, this is a polynomial function of r. It varies as r squared. This also varies as r squared because this r is being multiplied with an r. So if n equals 3, you have an exponential decay multiplied with some function, some polynomial of r squared. For r equals 2, you have an exponential decay multiplied by some polynomial of r. Here you have n equals 1, so you have an exponential decay multiplied with a 0th order polynomial of r, which is just a constant. So this is a general scheme that is obvious from these solutions. Alright, now we focused on this radial part in the previous lecture. We actually drew this wave function. Let me draw this again so that I can reiterate some important concepts. Any questions? कोई सवाल? जी. Good question. Is there a specific value for A0 or is it just arbitrary? It's actually there's a specific value for A0 and we're going to derive this in a minute. It's a simple calculation, we can derive A0. But first of all, let's look at this top wave function here. This is the radial part of the wave function for n equals 1 and L equals 0. R 1, 0. This is the value of the quantum number n. This is the value of the quantum number L. And it's a function of R. This is some constant. I don't care about the constant for the time being, so I just write K, capital K. This is a specific constant, but I just write it K, e raised to minus R over A naught. And in the previous lecture, we actually did plot this wave function. This is just an exponential decay. And we also motivated ourselves of the fact that this does not show the probability density. If you want to talk about the radial probability density, you have to take into account the volume measure. And when we were able to do that, the radial probability density turned out to be a function that varies like this. So this is a plot of the radial probability density, which is the probability of locating the particle at a certain radius per unit radius. Okay? So you always find probabilities per unit volume. So this is the probability of locating the particle within a certain shell outside the nucleus. And it turned out to be equal to 4 pi small r square capital R. This is what I call the radial probability density, which depends upon R. This small r represents that I'm talking about the radial probability density. So this is really a plot of the following thing. I have a nucleus, and I'm outside the nucleus, and I take a small shell, an infinitesimally thin shell, really thin. And this shell is at a radius r, and the thickness of this shell is tiny, minuscule, dr. And I would like to find out the probability of locating the electron inside this shell. This is a meaningful quantity. I always find out probabilities in small volumes. So I want to find out the probability of locating the electron inside this shell when the electron is in this state. Alright? So when I find out this volume measure is simply 4 pi r square dr. And per unit radius it turns out to be 4 pi r square. So this is the probability density, the radial probability density. So I multiply this r with a factor of r squared, I get a curve like this. This actually tells me that there is a maximal probability density of locating the electron somewhere, and it turns out to be A naught. How do I find that? I find that by taking this r and multiplying with 4 pi r squared. Let's do that. For this shell, or for this value of n and L, which is the ground state of the electron, PR is 4 pi r square multiplied with, this is actually 4 pi r squared r modulus squared. 4 pi r square r modulus squared. So this is 4 pi r square. I take the square of this, k square e raised to power minus square of this 2r over A naught. So this is the radial probability density. Yes. This r, all of this. So I have a wave function psi, which is the solution to the Schrodinger equation. This is a function of r, theta, and phi. Do you understand what r is? Okay, theta, phi. Now this wave function has been factorized into 3 components. One is the radial part, which depends upon r. One is the polar angular part which depends upon theta, and one is the azimuthal part which depends upon the azimuthal angle. No, it depends upon theta and phi as well. So what I'm suggesting here is that if I'm at a distance r, irrespective of what the angular probabilities are, I just make a thin shell at radius r, what's the probability of locating the electron in that shell? That will only depend upon capital R. Because I'm taking all possible angles here in this shell, I have all possible angles covered. Theta goes from 0 to pi, phi goes from 0 to 2 pi, so all possible angles are covered. So I'm hiding away the angular dependence because I'm including the angular dependence. I'm just taking a thin shell, a veneer of a shell at a radius r. So all angles are included. Okay? So now if I take this function PR, how would I find out where is this function maximized? I take the derivative with respect to r. So I want to find out the radius at which this function is maximized. So I take the derivative of the radial probability density as a function of r. Now 4 pi k squared is just a constant. Now first of all I take the derivative of this 2r, and the exponential factor just carries along, comes for the right. Then I take r squared and I take the derivative of this exponential function minus 2 over a naught e minus 2r over a naught. And I posit that this equals 0 because I would like to find out the maximum of the probability density. Now I solve this algebraic equation. This can't be 0, so this has to be 0. The exponential factor can never be 0. E raised power something is never 0. So this means that the probability density is maximized where 2r minus 2 over a naught r squared equals 0. And this actually shows me that this is maximized when r equals a naught. So a naught is actually a value of length. It has dimensions of length. This is length, so this must also be length. So exponent of a dimensionless number. A naught is also some length. At this a naught, the probability density is maximized. So if I have an electron in this so-called orbital in the ground state with n equals 1, l equals 0, and I try to locate where the electron is. So I have a microscope. In fact, such an experiment was indeed performed in 2013, just 5 years ago. I have an electron. Since I would like to specify the electron by an electron cloud which has a wave function that is smeared out in space, and I take a thin veneer of a shell at a radius r, the probability of locating the electron is maximized if this r equals a naught. Whatever that a naught is, I'm going to tell you what the value of a naught is. Okay, so this is a naught. This is called the Bohr radius. It's like a unit of length. Just like the electron's charge can be considered to be a unit of charge, the magnetic moment of an electron can be considered to be a unit of magnetism. This Bohr length can be considered to be a unit of length. Okay, it's a fundamental unit of length. So this is where the probability density is maximized. And something strange, something nice that you observe about this probability density is that it's not symmetric about a naught. The first thing that you observe is that the density is 0 at the nucleus, which is good. This satisfies Heisenberg's uncertainty principle, because the closer you get to the nucleus, you're confining the electron, its energy goes up, and the electron is going to resist that. So there is 0 probability of locating the electron at the nucleus, even though this wave function, this bare wave function, shows that R is maximum, but probability density is 0, even though R is maximum. So you can't find the electron at the nucleus. This is forbidden for the electron, and this is in good agreement with uncertainty. The second is that this probability density is not symmetric, and the way this density goes out, it has infinitely long tails. Even though this probability is getting smaller and smaller and smaller, but the tails are infinitely long. So an electron, technically speaking, you can find it anywhere if this electron is in the ground state. But the maximum, the modal probability, where the probability is maximized, is centered at A0. Okay? And the good thing is, can we come up with a value of A0? In fact, you can use Bohr's model and find out the value of A0. You can solve the Schrodinger equation, but there is a simpler trick to find the Schrodinger equation. Something that you already know, and that trick is the uncertainty principle. So let's see if we can have the uncertainty principle come to our rescue, and can it predict the value of A0? Let's find out if we can do that. Now we know that according to the uncertainty principle, the uncertainty in momentum, if I were to multiply this with the uncertainty in position, now we're talking about radial position, so I have R. So if you take this product, this is roughly equal to h bar, or h. Let's call it h bar. Okay, so this is an order of magnitude calculation. This means that my delta P is of the order of h bar delta R. Now what about the energy of an electron? The energy of an electron inside an atom is roughly given by the sum of its kinetic energy and its potential energy. So the kinetic energy is P square over 2m. That's the kinetic energy of an electron. Since the electron is the ground state electron, it's close to the nucleus, it's moving with non-relativistic speeds, so you can take the classical formula, P square over 2m for the kinetic energy plus the potential energy. So what's the potential energy for the electron? 1 over 4 pi epsilon naught E square, the charge on the proton inside the nucleus multiplied with the charge on the electron divided by R. And what sign do I have here? I have a minus sign here. Alright, so this is an estimate for the energy of the electron. Now this P, I would like uncertainty principle. I would like Heisenberg to tell me what this P is. This P has to be at least the same as delta P. If P is smaller than delta P, doesn't really make sense. So the uncertainty in momentum has to be at least the uncertainty in itself. Okay? So I just estimate my delta P to be equal to P, which is h bar over delta R. So if I insert this value in here, I would obtain h bar square 2m, and I replace delta R by R. This also makes sense by the same argument. Remember, I'm not putting strict equalities here because it's an order of magnitude estimate. So I'm being proper here. So h bar square over 2m R squared minus 1 over 4 pi epsilon naught E square over R. This is my estimate for the energy. Now can you use this expression to find out what is the most optimal R? Optimal means with this relationship, in a state of equilibrium, when everything is in its ground state, when everything is well behaved, it's in a natural resting mode, the electron, in the ground state, lowest energy state, how can I find R? Yes?
Approximate to 0.
By?
Approximate to 0.
We would like not to make, nothing can be 0.
Approximate to 0.
Uncertainty principle says that nothing can be 0. But it has to be a minimum value. Okay? So we would like the energy to be minimum. This means we would like to find out the R which minimizes the energy. In that particular calculation, we found out R that maximizes the probability density. But that did not give us the value of A naught. It just told us that R should be equal to A naught. And A naught is the factor that we put in here, which tells us about the decay of the wave function. But now we would like to find out the value of A naught. So it's not arbitrary. So I would like to find the derivative of this energy with respect to R. So if I were to do that, dE over dr is h bar square 2m. Now the derivative of 1 over r square is, I think, minus 2 over r cube minus 1 over 4 pi epsilon naught e square. The derivative of 1 over r is, I think, minus 1 over r square. I put a plus here, 1 over r square. Now I can solve this for r. H bar square over 2m r cube equals e square 4 pi epsilon naught r squared. So I get rid of one r, and my r, which minimizes the energy, equals 4 pi epsilon naught h bar square over 2m e squared. It just goes to the other side, becomes positive. I equate this to 0.
You said the 2 should be cancelled.
Okay? So this is the R that minimizes the energy. This is actually A naught. This gives me the value of A naught. Now by plugging in these fundamental constants, I can find out what A naught is, and this is 0.529 angstroms, 0.0529 nanometers. So this is how I can estimate Bohr's radius. Now if I were to plot these higher order functions, these functions, just the wave functions, how would I do that? I can just take a computer program, plug in the radial wave functions and make a plot. That's what I would expect you to do. Every modern physics should be able to make a plot. Alright, so if you observe here, this solid curve represents what I've drawn on the blackboard. The radial part of the wave function for n equals 1, L equals 0. For n equals 2, L equals 0. I obtain this function here, this dash function. For n equals 2, L equals 1, I obtain a dash dot function, dash dot, this function. For higher order wave functions, for higher values of n, for example, for n equals 3, L can take up 3 values, 0, 1 and 2. So I get, for L equals 0, I get this. For L equals 1, I get this. For L equals 2, I get this. One thing that you observe is that the wave function has 0 crossings. For n equals 1, l equals 0, there are no zero crossings. For n equals 2, l equals 0, I have one zero crossing here. So the number of zero crossings changes with L. And if you look at the polynomial function here, this is simple calculus 1. This function never crosses 0. Alright? Now what about this function? This polynomial does cross 0. It has a zero crossing. How do I find out the zero crossing? I just take this polynomial equated to 2. Equated to 0. When I equate this to 0, at a value of r equals 2a naught, it will cross 0. And this is what we observe here. At r equals 2a naught. So this is 2a naught actually. So look at this axis. This is 2 times a naught. This is in units, calibrating units of a naught. So at 2a naught, which is this point, at this point, 2a naught, this radial wave function goes to 0. It crosses 0. So the polynomial tells us how many nodes are inside this radial part of the wave function. The number of nodes is n minus l. So here, for this dash function, n equals 2, l equals 0, n minus l is n minus n, it's n minus l minus 1. So this is n minus l minus 1 is 1. So this wave function has one node. The number of nodes is n minus l minus 1. You observe this here as well. For n equals 3, l equals 0, there are two nodes. Because 3 minus 0 minus 1 is 2. Look at this solid line. One node, second node. And this is because the polynomial part of the wave function has two roots. It has two zeros. So by looking at the radial wave function and the polynomial part, you can see that this wave function has certain nodes. Please pay attention. There are certain number of nodes, just like a standing wave. Now there are no boundaries, but the system is again bound. The electron is inside a potential. It's akin to a bound system, so it must behave like standing waves. And these standing waves are just the wave functions. So far, so good. Now you can plot these wave functions up with arbitrary orders. For n equals 32, for n equals 16. But those wave functions get more and more complicated and they don't give you any physical insight. So I've only chosen to reproduce the simplest of these radial wave functions. Now these radial wave functions are good, but more important are the radial probability densities. Now if I take the modulus square of these wave functions and multiply them, each one of them with r square, I get these radial probability densities. Now you observe that this orbital, the n equals 1, l equals 0 shell or orbital or wave function has a hump at a naught, 1 times a naught, which is just what I've drawn over here. The higher order, n equals 2, l equals 0, l equals 1, have humps that are further away from the nucleus. So if an electron is in a higher excited state with a higher value of n, its position is, the probability of locating this electron is further away from the nucleus. So an excited electron has to exist predominantly further away from the nucleus. It can still exist close to the nucleus. Look at these small probability densities near the nucleus, but the highest electron probability is further and further away from the nucleus. And again, you could take the probability density, differentiate with respect to r, and find out where the maximum probability density is. You will get these humps, these modal points where the probability is maximum. So these are plots. Once again, the probability density has some nodes, some locations where you can hardly find an electron. Now, the strange thing is that space is becoming quantized. All space is not the same. There are certain locations, for example this location, where if an electron exists in this orbit, n equals 2, L equals 1, there is zero probability of locating electron inside this region. So space loses its symmetry somehow. Even though we would assume that all space is the same, if I stand here, it doesn't make a difference if I move and stand at another place. However, quantum mechanics, being a bound system, having a potentiality less than the kineticity less than the potential energy, being close to a nucleus, having an interaction with the nucleus, dictates that space is not all the same. Some regions in space are more likely than others. So the isotropy, the homogeneity of space is broken. And this is something extremely powerful about quantum mechanics. Bohr's ideas or the old quantum theory or classical mechanics cannot give you these astounding results. And these results also match our experiments. There was a microscope that was invented in 2013 called the Heisenberg microscope that can actually image these probability densities, and I would encourage you to look this up. So this is the probability density for higher orders and so on. You get more nodes, etc. Any questions about the radial probability densities? Yes. Yes. But then you have to take into account the angular part as well. So, yes, these constants that come out here are because of the fact that you like to take the modulus square of r square with the volume element and integrate over infinity. That should be equal to 1. This is what gives you these normalization constants. Okay? And you can integrate over infinity because the wave function is actually decaying with distance. So it's easy to integrate over infinity. When r is infinity, this exponential function has decayed to 0. So you have a bound function. You can integrate. Sorry? समझ नहीं आई? You can test this, yeah. Oh, you'll be tested on this. Okay. On what? Your question is a valid question. I'm not asking you to perform a calculation, but it's a conceptual question. You can be tested on it. Yes. Yes.
The electron bound in atomic electrons just theoretically bounded in potential, are they like similar?
Yes, so it depends upon the form of the potential. This potential is an electrostatic potential which has 1 over r dependence. You can have other kinds of potentials, an r square dependence that gives you a harmonic potential. You can have an infinite well which has 0 potential. It all depends upon what form of potential do you have.
Like we equated with the energy equal to totality minus the potential. So would this system can we calculate the other formula x square, h bar square,
We've already looked at the formula for this system, which is minus 13.6 electron volts over n squared. Yes.
The whole it is 0 parts or radial. Is that part also known for not?
That can be considered to be a node, yes. But technically speaking, it does not qualify as a node. When I say n minus l minus 1 nodes, it's nodes outside r equals 0. It's nodes besides the nucleus. Alright, now nice thing. Okay, sorry. Darkness again. Now we paid so much attention to the radial part of the wave function that we've been blinded in a way from the angular part of the wave function. But the angular part is equally important, and we cannot drag it under the carpet. It's there. So what about the angular parts? And the angular parts are nice because we can make nice diagrams, and these correspond to what you are familiar with, that is orbitals. Now, if you look at, don't be confused by these y's. These y's are just a combination of theta and phi. So some authors would like to lump theta and phi together and write them as y, capital Y. Y is a function called spherical harmonic function. Now each one of these y's depends upon L, and now for the first time ML makes an entry into the discussion. So one of these quantum numbers, the top one is L and the bottom subscript is ML. For a given L, there are two L plus 1 values of ML. This is something you all learn from chemistry, so I don't want to belabor this point, but what I want to emphasize and reiterate is what do these functions look like in space. So let's consider this function. First of all, the simplest one. So all of these are solutions to the Schrodinger equation. You lump this together with the radial part, you get the complete wave function. Now we would like to see how these wave functions look like, because these wave functions, when you take the modulus, going to tell us simply about the probability of locating the electron in an experiment. So let's plot these one by one, just the simpler ones. And I also like to talk about lasers today. So look at the top left wave function, which is, so the angular part of the wave function is theta, which is a function of small theta, phi, which is a function of phi. Now this theta depends upon L and ML. This phi depends upon ML, only on ML. So the simplest angular part of the wave function is when L equals 0. When L equals 0, ML can only be 0. So I have, when L equals 0, ML equals 0. So I have theta 0, 0, phi 0, phi. Now all of this is lumped together on this table, which is available on our website as Y. The product of theta and phi has been labeled as Y. 0, 0. This is L, this is ML. Now placing these indices as subscripts or superscripts are just conventions which different authors follow. You can put 0, 0 as well. Now this becomes a function of theta and phi. Now this is just for these values of L and ML. This is just a constant. Let's call this constant A. It turns out that for these values of L and ML, there is no dependence upon theta and phi. Right? You can have a function of x. Function of x equals 1, equals 3. It does not depend upon x. So it turns out that for these basic values of L and ML, there is no dependence on theta or on phi. Simple, yes. I'll come. So if this is plus ml minus ml, you have minus and plus here. So plus ml means you get this minus sign, or this negative you get this plus sign. Okay? Now I would like to look at that simple wave function and I would like to plot it. L equals 0, ML equals 0. In chemistry, you would call L equals 0 and S orbital. S orbital. Now if I would like to plot this, there's no dependence upon theta and phi. Actually no dependence. So if I would like to make a Cartesian axis, x, y and z. If I would like to diagrammatically represent this wave function, how would I draw a contour, a surface on this 3D plane which has no theta or phi dependence? Yes? It will be a sphere. We don't know the radius as yet because there is no concept of radius so far in this angular part, but it's a sphere. A sphere is spherically symmetric. You look in any direction, any angle, the sphere is just the same. So a sphere is the only object that has perfect spherical symmetry. Spherical symmetry means no dependence on theta nor on phi. So I can represent this by a circle, right? So this is what is conventionally drawn for an S orbital. This is theta 0, 0, phi 0, phi, or the S orbital. This is a picture. Now if I take the modulus square of this, it remains a sphere. Now generally there are different ways of plotting this. If I were to combine this with the radial part, if I took this part, suppose n equals 1. For n equals 1, I can have nothing but L equals 0 and ML equals 0. So I'm taking this orbital part and I'm going to multiply it with this wave function. That's what I need to do because I need to combine the radial part with the angular part. Now, conventionally, what is drawn is a probability density. So I take the radial probability density. The angular probability density is just going to be constant. It does not depend upon theta or phi. So if I took the modulus square of this, it's just a constant, another constant that is independent of theta and phi. So if I took the angular probability density and I took the radial probability density and multiplied point by point, I can draw a diagram that starts looking like what you're familiar to seeing in chemistry textbooks, which is an orbital diagram. Let me draw that. I'm going to draw dots representing a probability density. So just everyone has to be slightly patient here because this is going to take me some time. This is what the electron cloud actually looks like. And this is what you're familiar to seeing in chemistry textbooks. At a certain radius, which is qualifies as A naught, there is maximum likelihood of locating an electron. So if I take this diagram and make a cutaway which means I just take a plane, say the YZ plane, and I look at the density of the dots that I've drawn, I get this thing. So there's maximum density, maximum number of points per unit volume that I've drawn at radius A0. But there is no dependence on the angles theta and phi. So this electron cloud picture, which is an S orbital, which represents an S orbital, is also represented in this fashion. In a cloud picture, it's represented in this fashion. Now this means that if I were to perform an experiment, if I had a microscope, a Heisenberg microscope as it's generally called, which can locate a single electron in a single hydrogen atom, the density of these points tells me what's the likelihood of locating electron at a particular region. Higher the density of points, higher is the likelihood of finding the electron here. And then the wave function is going to collapse, usual quantum mechanics kicks in, and something that we've already seen. Okay? Now if I had n equals 2, L equals 0, ML equals 0. If I had the same orbital, the same angular dependence, but my radial probability density has changed. So now I have two lobes. Now I have a radial probability density that actually looks like this thing here. Oh, sorry, this thing here, this thing. Then the location of the maximum probability has shifted further away from the nucleus. So then, but the angular dependence remains same because L equals 0 and L equals 0. So there is no angular dependence. The angular dependence is that there is none for this orbital. So now I have a 2s orbital. So for a 2s orbital, if I were to draw the 2s orbital on the same scale, this is my x-axis, y-axis, z-axis. If an electron in a hydrogen atom were excited to the 2s orbital, still there would be spherical symmetry, but instead of being A0 here, you would have 4A0. So the electron will be spread out further in space. So there will be maximum likelihood of locating the electron here at 4A0. So this is the diagram of the 2s orbital. And so on. So the probability density is going to bulge out, it's going to dilate, it's going to bulge out. The electron is further out away from the nucleus, but there is perfect angular symmetry because still we have an s orbital. Now things get more interesting if you actually move to, yes, would there be? For n equals 2, L equals 0, ML equals no. But for L equals 1, ML equals 0, there is going to be a no. To the graphs. Okay, let me first answer his question. What if n equals 2, L equals 1? Is this what we have? N equals 2, L equals 1, ML equals 0. For this particular combination, when I have n equals 2, L equals 1, I have this thing here, R21. So R21 is, the probability density is plotted like this. Alright, I'm sorry. This is n equals 2, L equals 1. So what I've drawn here is actually this thing. if I were to plot this, n equals 2, L equals 0, ML equals 0, I would have look at this radial probability density with a node. Okay? So if I were to plot this on the same graph, I will have a maximum probability density at some location in between. I have another location of some semi-maximum probability density and higher probability density here, and I will have a node in between. Okay? Alright, so you had a question about the, you're fine? Alright, so let's take a 10-minute break and then we're going to move on to the more complicated orbitals.